When a fast-moving object rips past a tree, the leaves shouldn't just fall due to gravity. They need to react to the invisible vacuum of air trailing right behind it. Brute forcing this with standard noise fields or pop forces looks mechanical. We want to avoid this. Doesn't look good, right? So let's fix that. So today, we are building a custom wind tunnel style force in Houdini to make our leaves fall naturally. A prerequisite for following this tutorial is that you actually need to have a tree model. We need it to isolate our leaf geometry and extract points from it. So, the plan is split into 3 phases. First, we take that static point cloud from our leaves. Second, simulate a custom wind field. And lastly, feed them both into a pop solver to let physics do the heavy lifting. We aren't simulating full leaf geometry. We are using a smart workaround, isolating the leaf segments from our tree mesh, running an extract centroid node with a piece attribute via connectivity, and caching out a single point for every single leaf. Now we use object merge to import our leaf points so we have a single point for each leaf. Then we need to compute their initial velocity. Drop a trail node. Set it to central difference and check evaluate within frame range to get v-vector data right off the bat. We don't want to simulate dead weight, so we isolate and delete slow points. In an attribute wrangle, we calculate the magnitude of the velocity vector and compare it to a minimum speed flow parameter. If it's too slow, we dump it into a blast group. Now, drop a blast node to delete those group points. Pro tip: it is generally much faster for compute to use a blast node here instead of running a remove point function. To keep things clean, you can optionally drop a group delete and attribute delete nodes to wipe out any temporary data we don't need. Lock it down with a file cache node so we have a solid foundation before jumping into the volumes. Next, we create the wind field. We are running a smoke simulation emitted from our moving kaleidosphere. In my production files, sphere as a collider perfectly matches an RBD simulation of the tree getting smashed by this sphere, but you can use a rubber toy or a displaced sphere to experiment. Drop a normal node to store n on your points. Right after, drop a trail node set to compute velocity to generate velocities per point. We will need this normal and velocity data later to calculate our custom shape following velocity. Now, scatter points across the sphere. Turn off relax iterations. The spacing doesn't matter for the setup, and disabling it cuts out useless compute time. We want to emit air when the sphere is moving, and stop when it slows down to realistically simulate displaced air. If your animation uses Bezier interpolation, your object will slow down instead of stopping abruptly. You can drop an attribute randomize node to vary the velocities. Copy-paste our speed threshold wrangle and blast setup here to cull out the slow points. Remember, always refer to Houdini's help documentation if you ever need to double-check a function syntax. Optionally, we can clean any groups we don't want anymore to keep the setup clean. Next, place Pyro source node to create the necessary attributes for this smoke simulation. Time to turn points into volumes that the Pyro solver will actually read. On the left, drop a volume rasterize attributes node for density and temperature. Turn on velocity blur with a shutter of 1 and offset of -1 to smooth it out. On the right, drop a parallel rasterizer only for velocity. Turn off velocity blur here, but turn on normalize by clamped coverage. Merge them together and file cache it out. Because this isn't a solver yet, uncheck the simulation toggle. Now for the absolute crown jewel of this entire pipeline, creating a custom wind tunnel effect using orthogonal vector decomposition. Instead of letting the smoke just trail lazily behind the sphere, we want a physical force field that actively condenses volumes and shoots in front of our object, following its exact geometric contour. First, what is this workflow trying to achieve? Suppose we have a surface, think sphere surface, a normal on that surface, a direction of movement, aka our collision sphere velocity. The problem: the movement direction C contains some motion going into or out of the surface, and some motion going along the surface. We want to separate these. Why? Because for this effect we want particles to slide across geometry instead of simply inheriting raw velocity. The board is solving a classic projection problem. We start with what's known, normal n, direction vector C. We want the unknown, parallel component and perpendicular component, such that C equals C parallel plus C perpendicular. This is called vector decomposition. Why can't we immediately calculate the parallel vector? Because we only know n, which tells us direction, but we don't know how much of C lies in that direction. For example, if n is 1 unit in y-axis, that could produce any value in y-axis, 3, 10, or even -5, all parallel to n. Which one is correct? We don't know yet. That's where we introduce beta. We say C parallel equals n beta. This means that the parallel vector must be some scale version of n. Beta is unknown. This is not the solution, only an assumption that will allow us to do further calculations. We are saying if the parallel component exists, it must lie somewhere along n. Next, we need to find perpendicular component. Considering we now have a parallel component n beta, whatever remains must be C minus n beta. This is our candidate perpendicular vector. At this point, we don't know beta. Therefore, we don't know if this vector is actually perpendicular. Important observation is that dot product between two perpendicular vectors equal to 0. So we enforce n dot the quantity C minus n beta equals 0. This is the entire trick. On a side note, why dot against n? And why not against n beta? Because n beta points in exactly the same direction as n, scaling does not change direction. Using n just gives simpler algebra. Same geometric meaning. Let's solve for beta. First we distribute, pull scalar beta outside and solve. This is projection. What did we gain by doing this? Now we know exactly how much of C points along n. And finally, this is our parallel component, as well as the perpendicular component. Another tip, why is n, t, aka n transpose, written on the board at the end? It's just another way of writing dot product. When multiplying n and c, which are obviously row vectors, but at the same time 1 by 3 matrices, we must transpose one matrix. Otherwise, we can't multiply them. In practice, this doesn't mean much because there's dot function in Houdini. This gives us two useful vectors. First is normal motion, which shows how much motion penetrates the surface. Second is tangent motion, which shows how much motion travels along the surface. Why use projection instead of simpler methods? Why not dot product only? Dot gives a scalar, not a direction. Why not flatten y? Only works on flat ground. Why not connect trail node to this point wrangle where we define a function that accepts two parameters, n, the surface normal, and c, our velocity vector. Next we write out formula for the parallel component. Then comes the formula for perpendicular component. We don't have to type out the entire formula. We can simply reuse vector variable named parallel. Then we normalize perpendicular so we only get direction. Then we actually use the function we just created by filling in the arguments. Then multiply normalized direction until it looks good. You can come back later and change this number once we build out the rest of the setup. Next we want to create scatter points and displace them away from the surface of original mesh because we want to have a force field in broader area around the mesh. This code randomly displaces points along normals. To break up the uniformity, drop an attribute noise node set to a zero-centered range, tweaking the amplitude and element size to get a gritty, organic look. Next, we generate our volumes. Drop a bound node, follow it with a volume, and set the rank to vector with the name cval, short for custom velocity. Set uniform sampling to by size. Now, wire that into a volume from attribute node, feeding our noisy, peak points into the second input to transfer that custom velocity directly into our cval volume grid. Pay close attention here. Default Houdini volume split vector fields into 3 independent scalar components, x, y, and z. If you feed that straight into a Pyro source node, it's not going to work. Drop a convert VDB followed by a VDB vector merge to consolidate those separate fields into a unified VDB vector block that the solver can actually read. Merge your primary file cached volume emitter with your custom cval field and pipe them into a Pyro solver. Under the sourcing tab, disable the default flame behavior and explicitly add an entry to source our missing cval data alongside the standard density, temperature, and velocity fields. Under the Fields tab, adjust your dissipation to control how long the vacuum lasts. In the Shaping tab, kill the buoyancy so the air doesn't rise like hot fire, and dial in your disturbance, turbulence, and shredding. Pro tip, always turn on your shape guides here. It lets you visually map the exact micro and macro scales of your noise forces relative to your geometry so you aren't guessing in the dark. Cache the solver to disk. Jump back over to your original cached leaf points branch. Drop a split SOP setting the group to at name equals density and separate into two distinct null SOPs, one dedicated strictly to density and the other strictly to your velocity field. Drop a pop network. Plug your cache points into the first input, your volume density into the second, and your volume velocity into the third. Dive inside. Leave the pop object and pop solver completely stock. On your pop source, change the emission type to points and set it to use first context geometry. To turn this from a basic simulation into a cinematic shot, add a pop interact. Pop interact is your secret weapon here. It forces close particles to push against each other, completely eliminating those artificial, ugly stringy clumps that completely give away a cheap particle simulation. Then add a subtle pop force for secondary microdetails. To finally bind our leaves to our air currents, drop a pop advect by volumes node. Switch the velocity source dropdown to third context geometry to sample that beautiful, orthogonalized VDB velocity field we built, and crank up the velocity scale to taste. If your source points already carried inherited velocity from a previous RBD impact like mine did, it will seamlessly layer together here. Finish off with a gravity node. And add colliders as you wish. Use static object or ground plane node. Once you exit the pop network, it's time to prep our simulated points for final geometry instancing. Drop an attribute delete and a group delete node. We want to strip away all the simulation junk and explicitly keep only 3 attributes: velocity v, unique particle ID, and age. Keeping your data stream lean is important. Lock the simulation down with a file cache node so your viewport stays blazing fast. Next, we create a randomized p-scale attribute to naturally drive the scale variation of our leaves. Right after, drop an attribute randomize for your orientation, create orient attribute and set distribution to direction or orientation. If you copy geometry onto these points now, they will glide through the air like stiff cardboard cards. To fix this, we are building a dynamic transformation matrix inside an attribute wrangle. First, we use Q-convert to turn our orientation quaternion into a raw 3x3 transform matrix called 3@transform. Then, we multiply that entire matrix by our float scale to bake our random sizes directly into the transformation. Now for the magic line, the rotate function. Instead of spinning the leaves at a constant speed using @frame, we use the literal magnitude or length, v@v, of our velocity as the angle, and the normalized velocity vector normalize, v@v, as our physical rotation axis. This means the harder a leaf is hit by the wind tunnel, the faster it violently tumbles through the air. As it loses momentum, the spinning naturally decays back to 0. To finish it off, we need structural variety. I have 6 unique leaf models prepared, indexed from 0 to 5. Drop one last attribute wrangle onto your simulated points track and use this vex snippet to randomly redistribute those 0 to 5 index numbers across your particle IDs. This overrides the linear particle sequence with a chaotic, randomized asset assignment. Keep in mind, both leaf stream and simulated particle stream must have ID attribute. Copy to points node will use that logic to connect leaves to our points. Wire your leaf variations into the first input of a copy to points node, and your simulated points into the second. Because Houdini natively recognizes 3@transform over standard scale and orient attributes, it perfectly applies our custom vex matrix scaling and velocity-driven rotation onto every single leaf instance instantly. Drop a final null node. With our custom orthogonal velocity and velocity-based tumbling locked in, we have a leaf simulation that actually reacts to the air displaced by our collider. It's a smart, lightweight workaround that avoids heavy geometry until the very last step. Take this template, swap in your own assets, and see how much detail you can push into your next project. If you want to stay connected with the long-term vision of Olympex Productions, see what commercial work we are dropping next, and get a behind-the-scenes look at our work, follow our journey on social media.